Hello, good afternoon. Today we will go over Fall 20 Math 227 Test 4. Let me remind you that your test will be next Wednesday, next week from 1 week from now, and it will cover hypothesis testing. It will cover hypothesis testing, chapter 10 and chapter 11. Okay, let's start. Yeah, with you, I go over Fall 20 Test 4 with my Friday class later on. I will go over Winter 21. I think these two are good representation of type of question I will ask you in your test. Let's start. Number one, according to a survey, 85% of American adults eat salad at least once a week. Now, a nutritionist suspects that the percentage is less than this, so less than 85%. Now, she conducts a survey of 200 American adults and finds that 167 of them eat salad at least once a week. Conduct the appropriate test that addresses the nutritionist's suspicions. That is the percentage of American adults, the claim, the percentage of American adults eating salad at least once a week is less than this, and this is 85%. Okay, in step 2, hypothesis. Null hypothesis, alternate hypothesis, P is less than 85%. Otherwise, greater or equals to 0.85. Or you can also use equal sign for the null hypothesis. Now the claim is here. This is the claim. And from there you see that's a left tail. Okay, the one I write in red, you don't need to show. The one I write in blue, you have to show. Test statistic. %. So we use C-scored. Oh, what is the p-hat? P-hat is 167 over 200. 167 over 200. That's 0.835. No, that's 167 over 200 is, yeah, 0.835. Okay, so this will be 0.835 minus 0.85 over square root of P Q over N, which is 200. Now, because the P is 0.85, then the Q will be 1 minus that. Okay, now then I will use my calculator. I get negative 0.594088809. Step 4, p-value. That's standard normal distribution, negative 0.59409. The p-value is the area of that tail. That's p-value is normal CDF, negative E99, negative 0.5940901. That is 0.27623. That's the p-value. Now, if you want extra credit, that's why if you see here, the number of points for this test is actually very low. But that's because I have extra credit 1 point for every critical value you get. So if you get all critical values, then there will be around 7 or 8 points coming from there. Okay, so PB, 4B, critical value. The alpha, I believe, is 0.1 or 10%. The alpha is 10%. So the critical value you need 10% here. So T critical is inverse norm, area to the left, 0.101. I'm sorry, not TC, it's Z critical. It's C, not T. So C critical is negative 1.28155, which is to the left of test statistic, right? Which is to the left of test statistic. Okay, now step 5, informal conclusion. Informal conclusion, fail to reject null hypothesis. Okay, now finally, step 6, conclusion. At alpha equals to 0.1, there is insufficient evidence to support the claim that the percentage of American adults eating salad at least once a week is less than 85%. Okay, now the thing is, the sample data does not support that claim. Okay, now that's for number one. Let's see number two. A machine fills bottles with 64 fluid ounces of liquid. Now, the quality control manager determines that the fill levels are normally distributed with this mean. The mean is 64 and standard deviation 0.42. Now, he has an engineer recalibrate the machine in an attempt to lower the standard deviation. Okay, now after recalibration, the quality control manager randomly selects 19 bottles from the line and determines that the standard deviation of these 19 bottles is 0.38. Is there less variability in the filling machine? Claim there is less variability in the filling machine I think I want to add after recalibration. Okay, now hypothesis. Now our sample standard deviation is less than 0.42. But does it mean the new standard deviation is less than the earlier one? Okay. And here we see that again, the claim is with the alternate hypothesis, and that's again a left tail. Now step 3, test statistic. We are testing standard deviation. Okay, so chi-squared equals to degree of freedom times sample variance. Don't forget, you need to square it because 0.38 is standard deviation, divided by population variance. That's 18 times 0.38 squared over 0.42 squared. I get 14.73469. Therefore, the p-value it's chi-square distribution, right? It's non-negative. Okay, the 14 point something is here, 14.73469. So the p-value is the area to the left of that, right? That's chi-squared CDF from 0 to 14.73469, degree of freedom 18. So chi-squared CDF, lower bound is 0, upper bound is 14 something, degree of freedom 18. I get the p-value to be 0.31990. Okay, which is less than alpha. The alpha is 0.03, right? The alpha is 0.03. So we will fail to reject null hypothesis later on. But before we go on, let's see what's the critical value. We need 3% here. We need 3% here. So chi-squared critical will be inverse chi, the area to the right, right? Inverse chi, you do 0.97, that's area to the right, and degree of freedom 18. Okay. Now you use the program. I hope you remember area to the right, 0.97, degree of freedom 18. So chi-squared critical is, oh, it takes forever with my calculator. I get 8.511985. Where's my test statistic? Oh, 14. So you see my test statistic is to the right of that. It's not on the tail. Okay, so again, we confirm that the informal conclusion will be fail to reject null hypothesis. Conclusion. At alpha equals to 0.03, there is insufficient evidence to support the claim that there is less variability in the filling machine. After recalibration. Okay, now you see it's kind of like pack, huh, when I write. So when you show your work, try to take a look if you may need to, like for example, my number 1, you may want to try to write a bit further to the left. Okay, but I also think that I may change my pages into 1 question per page so that you have more space. Okay, so how many pages here? This is 1 out of 7, right? 1 out of 7. So I may split this, the question number 1 and number 2, instead of 1 page. Later on, I make it into 2 pages so that you have more space to write. Okay, but I still need you to make it neat. Okay, clear and neat and systematic and understandable. Okay, basically do it my way. Okay, do it my way. When you write the claim, hypothesis, make sure you write the number too. Okay, the number and the title, number, title, number, title. Okay, including number 4, number, title. Now, do not write this number, title, and then you continue equals to normal CDF, blah, 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 blah. No, 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 no. Okay, that's for the title. That one is for the title. Let's go on with number 3. I think my number 3, page 2, only 1 question. Yeah. Travelers pay taxes for flying, car rentals, and hotels. A sample of total taxes paid for business trips in 8 randomly selected cities gives the following. So 8 randomly selected cities. So n equals to 8, right? Now find the mean and standard deviation. Make sure you show work and proper notation. Okay, that's from sample, right? That's from sample. So x bar equals to 672 over 8. That is 84. Sample variance, that is 8 times 58,034 minus 672 squared over 8 times 7. So 8 times 58034 minus 672 squared all over divided by 56. That gives me the sample variance 226.57143. Then the sample standard deviation will be the square root of that. Okay, so this is the sample mean and sample standard deviation. Okay, now part B, test at 5% alpha if the standard deviation of tax paid for business trip is more than $10. So step 1, claim. The standard deviation of tax paid for business trip is more than $10. So step 2, hypothesis. The standard deviation more than 10. Oh, so that's alternate hypothesis. The standard deviation is more than 10. The null hypothesis, therefore, the complement of that. This is our claim. Still, the alternate hypothesis is the claim in this case, and it is a right tail. Step 3, test statistic. Test statistic chi-squared equals to degree of freedom. The sample size is 8, right? So degree of freedom is 6 times sample variance, which is 226.57143. That's sample variance. You can use this sample standard deviation, but you need to square it. Well, now, if you square it, you get that number back, right? Over population variance 10 squared, which is 100. I get 15.86. Step 4, p-value. So it's a right tail for chi-square distribution. That's 15.86. So the p-value will be chi-squared CDF 15.86 E99 degree of freedom 7. Get 0.02643. Oh, what is the alpha? 5%. Oh, this is less than 5%. Therefore, let me do step 5 first. So, informal conclusion. Reject null hypothesis. Step 6, conclusion. At alpha equals to 0.05, there is sufficient evidence to support the claim that the standard deviation of tax paid for business trip is more than $10. Okay, the insert, let me use blue, green for be the critical value. That is, what is the cutoff on the right tail such that the area of that right tail is 5%. Okay, so chi-squared critical is inverse chi, area to the right, 0.05, degree freedom 7. I get 14.06714. What is our test statistic? Should be more than that. Yeah, 15 something. Our test statistic is 15 something, right? Which is on the tail of here, right? Okay, because the chi-squared critical is 14 something. Test statistic is already 15 something. Now that's for part B of this number 3. Let's see part C. Test at 5% again if the mean tax paid for business trip is $75. That's the claim. The mean tax paid for business trip is $75. Not more than, not less than, but is $75. Now that tells us this claim will go to the null hypothesis because it has equal sign, right? Mu equals to 75. Now the alternate hypothesis will be mu is not equals to 75. The claim is here, okay? But the test is two-tailed test. Step 3, test statistic. Yeah, I supposed to have still say that suppose the taxes paid is normally distributed because the sample size is less than 30, right? No, I didn't say that there, but the assumption is it is normally distributed. Okay, so test statistic. We don't know the population standard deviation for taxes paid, so we will use the sample standard deviation. The test statistic becomes T. P hat is 84 minus 75 over 15.05229 over square root of 8. Now make sure the line on the top is longer. I get 1.69116. That's the test statistic. How about p-value? That's 1.69116, the area to the tail, but I need to double because it's a two-tail. So p-value is 2 times normal CDF. Oh, I'm sorry, not normal CDF, T CDF. 2 times T CDF, 1.69116, E 99 degree of freedom 7. That is 2 times 0.06732 multiplied by 2. I get 0.13465. This is 2, 4 here. Okay, now the alpha is 5% and p-value is greater. So our step 5, I leave some space there for critical value, right? Step 5, informal conclusion. Fail to reject null hypothesis. Now the claim is with the null hypothesis this time, right? So the conclusion, we will try to reject the claim. If the claim is with the null hypothesis, then we will try to reject that. And in this case, we don't have enough evidence to do so. Okay, there is insufficient evidence to reject the claim. So remember, if the claim with the null hypothesis, we will try to reject that. If the claim is with the alternate hypothesis, we will try to support that. At least that's the wording commonly used in the conclusion. Claim that the mean tax paid, the mean tax paid for business trip is $75. So maybe it's not $75, but so far it's not too much different, right? Okay, maybe not, but we don't have evidence to reject that. Okay, because your sample mean is 84, which is different from 75. But according to our computation here, the p-value is 13% something, which means even if that 75% is true, if that 75% is true, the probability for that to happen is 13.5%. To have 84 sample, the sample mean of 84. Okay, now critical value for our extra credit. Oh, by the way, you can work your critical value after your number 6. You can put it anywhere after step 4. Okay, you can put it anywhere, because what I want to see is actually step 4, not step 4b. Now then I have t critical, but this time is 2 tail, right? It's 5% divided by 2, so it's 2.5% each tail. So the t critical will be plus minus, don't forget. In first t, the area to the left, 0.975, degree of freedom 7. I get 2.36462. Now notice that my test statistic does not fall in the tail. It's actually here. The test statistic is here, positive 1.69, right? That's my test statistic. Okay, right now it's 4:40. So you see that in 40 minutes, we do two pages. Okay, approximately 20 minutes per page. Approximately 20 minutes per page. Number 4, in a randomized control trial in a tropical country, bed nets were used in a way to reduce malaria. Now, this is including Indonesia. Now, among 343 infants who used the bed nets, 15 developed malaria. Oh, okay, so this is the one using bed nets. The sample size, 343. The number of children or the number of people, infants using bed nets, 15 of them developed malaria. Now, then the one without bed nets, the sample size is 294. 27 of them developed malaria. Okay. We can use this instead of using bed nets, change that to vaccine, right? Okay, and the axis will be the number of people catching the virus. Okay, so we compare people with vaccines, people without vaccines. Okay, which is actually, we need to be careful with that though, because what I know right now, the COVID-19, the virus is still mutating a lot. And in Indonesia, for example, currently there are 4 different strains of COVID-19 virus going around. So, and the thing is, the vaccine we get, I think that vaccine has the first 2 or 3. I'm not sure. I'm not sure about this. I think I want to say that the vaccines that I got, Pfizer vaccine I got last month, that was actually only covered the first few mutations of COVID-19. Okay, but we have new strain actually going around. So even though I personally, how to say that, I need to be careful that I don't want you to think that this is political view. No, this is not political view. I'm not trying to have political view in my class. Doesn't matter, but my view is on my students' health, right? Okay, my students' health. My view is mask is actually in the domain of personal right. So I don't think the government can enforce that. Now, I'm not saying business cannot enforce that. So if I'm the one having the store, for example, I can enforce, hey, you know what? You want to come in, you need to wear a mask. Okay. Yeah. Okay. I just don't think that the government has that right. Okay. Just like a store, I have the right to enforce mask, the use of mask when you are in my store. But once you go out, it's up to you. Okay. On the other hand, as a private citizen, I myself, okay, I will still wear mask even though I am already vaccinated, fully vaccinated. Okay. Why? Because there are some mutations out there that I may not get exposed yet through the vaccine. Okay. Not to say that even I already have the immunity, okay, simply because I have the vaccine doesn't mean I cannot contract the COVID. I may contract COVID, but because I have that, I am vaccinated, so the virus cannot get developed in my body. But it doesn't mean the virus will die either. Okay, the virus may mutate in my body, and unintentionally I spread it to somebody else. Okay, so even though I don't think, my personal view again, I don't think the government should enforce masks to private citizens, encouraging the use of masks is very appropriate. And I myself wear mask, even though I'm already fully vaccinated. Okay, of course, I don't wear mask at home, right? I don't think that's necessary. But when I go out, I, my wife, and my children will wear a mask. Okay, why? Because not only that we protect ourselves from virus going into our body, but who knows, we have the virus. Okay, we don't want to spread it to somebody else. Some people actually asymptomatic, right? Okay, and the third thing, okay, even though I am fully vaccinated, I have immune, I don't want my body to be the incubator for the new mutation for that virus. Okay, again, this is my personal view. Okay, I'm not, doesn't matter what's your view, you're still my student, I still love you anyway, and I hope, of course, I hope everybody stay healthy, right? Okay, just don't try to take unnecessary risks with your body. Okay, especially the reason you come back to school, you come to school is because you have big hope for your future, right? Okay, now if all it takes is to wear masks to reduce your risk of contracting it, why don't you just wear it? Okay. Oh, another one is this. I wear 2 layers of mask, actually 3. The one inside I have cloth. The one in the middle is the surgical mask, and then the one outside is also cloth, but it's more into it's a bigger one to make sure that it's well covered. Okay, basically to make sure that the 2 inside are in place. Now the surgical one usually have a little metal on the top for your nose, right? Okay, so that one, after you use that for a couple days, for me, I actually use that for 1 month. Okay, I use that for 1 month. I don't really go out anyway, so when I say 1 month, it may just translate into like around 10 times going out. Okay, and then after that, I throw it away. Now the cloth one, however, I microwave that. I microwave that for 10 seconds. I see if it is okay. then I microwave that further for 20 seconds. I don't heat it like I microwave that for 1 minute right away. No, 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 no. I make it 10 seconds and then another 10 seconds or maybe 20 seconds. Okay, now the one outside, I wash it. Okay, now you may say, but Thomas, can you really breathe? I can. Actually, at first, no. But so if you ask me that question like last year, I would say no, I have hard time to breathe. But at the same time, I also know, hey, you know what? It's just about getting used to it. Okay, it's just about getting used to it. My family members in Taiwan, in Hong Kong, many years ago, when they have SARS there, they already start wearing masks even when there's no pandemic. So they wear masks every time they go out. And they were the one told me, hey, you know what? It's about getting used to it. Okay. And the fact that we will forever wearing masks when we go out, at least for the next couple of years, wearing masks when we go out, it seems to be a given. It will be the case, at least for me. Okay. Does it mean I will never get a fresh air anymore? I do. Like around 10 o'clock at night, I go out to my to outside and then I walk around without mask if nobody's around. If I see somebody's within like 30 feet from me, I start wearing it. By the time that person is within 10 feet, I already having my mask on. Okay, but anyway, it's not about government mandating us to wear masks or not. It's about how do you protect yourself. Okay. Since the beginning, I actually post something on my Facebook last year around March. I say that since when the responsibility, the burden of taking care of your health becomes government's responsibility. No, it's yours. When you get sick, you get sick. Okay, now with that in mind, don't think the government mandate, the county mandate as a restraint, okay, but that's for us. Okay, I don't like the fact they use the word mandate, okay, but I still use it. Okay, it's just like in the end, it's about me, right? Unless if you wear mask and it has a negative effect on your health, I know some people have that condition, then don't. Okay, then don't. Again, I say this not to share my personal, I share my personal view, but not to enforce that on you. Okay, I want you to stay healthy. Okay, if not wearing masks and not getting vaccinated will keep you healthy, so be it. Okay, yeah, so be it. Somewhere in the past, this is a bit off topic. Somewhere in the past, I think I shared with you that I am actually for vaccine. Okay, I'm actually for vaccine, but for this COVID vaccine originally, for this COVID-19 vaccine, originally I didn't want to get vaccinated. Okay, now let me tell you why. Okay, for people at my age, around 40 to 45, okay, most of us actually asymptomatic. Okay, so we tend to have a stronger immunity. Okay, the probability to catch COVID is actually only around and show symptoms only around let's say 3%. Okay, now and then the probability that people at my age, if I catch COVID and end up dying, is approximately I think 0.3%. It's a very small percentage. Okay, it's like this. The probability that I don't catch COVID and die is still higher. Okay, die because of accident, let's say. Okay, so computing the probability I catch COVID and die is approximately 0.009%. Not percent, 0.0. Oh yeah, that's right. 0.9%. So it's very small, very small. The probability that I end up having a very bad side effect because of a vaccine is actually higher than this. It's higher than this. In other words, the probability for me to catch COVID, and given I get COVID, I die because of that, is less than the probability I took the shot and develop very bad side effect. Now that is much higher. Okay. Now, but then, so that's the reason I didn't want to take that vaccine originally until my ophthalmologist, when I went to see my eye doctor, he actually changed my mind, saying that, Thomas, it's not really that at the end you die or not. Honestly, he said that to me. He knew that I'm a stat person, so he said that if you die, Thomas, that's actually fine. Why? Because you must have insurance. You must have life insurance. You must be so stupid. He said this to me. You must be so stupid that you are a stats instructor, but you are not insured while you are the only breadwinner for your family. That's super silly, right? So if you die, you're okay. Your family is covered. Okay. The problem is, what if you get disabled? You don't die, but you cannot work. Then instead of being the breadwinner, you are actually the one who take away the breads. Basically, you are the one actually take the resource away from your family. At that time, you must feel really, really bad. Now, with what he said, then I actually went back to the paper and I found that people who are vaccinated, the probability they die because vaccinated is actually very small. Okay, they actually very small, but how to say that? The thing is, like, they don't get really bad. Okay, so the percentage of people hospitalized due to COVID. So once you get vaccinated, you may get the COVID, you may catch COVID, but the chance that you get hospitalized after that is extremely small. It's extremely, extremely small. Okay. Now, of course, some people actually die because of that. They have a sudden change in their health, like suddenly just go really, really bad. Okay. They didn't get rest. They catch COVID. They didn't rest. Okay. In my opinion, COVID is just a flu. Okay. You need to rest though, full bed rest. I talk too much about this, but that's why I changed my mind. Okay. So the issue is not if I die because of vaccine or because of COVID, but what happens if I get disabled? That's what we don't want to happen. Okay, the side effect of COVID exposure without vaccine is much worse, much worse compared to if you are vaccinated. Okay. One last thing I would like to share with you is some of my family members, actually two of my family members, not really close, but I can say it's my mom's cousin. Two of them passed away because of COVID. Okay, one of them actually vaccinated, fully vaccinated, and then still died because of COVID. Okay, so what I want to say is, like, no, having vaccinated is not a guarantee that you will survive. No. Okay, but you need to take care of yourself. Really, really rest. Don't think that I'm vaccinated and I will be fine. No. No, vaccination only to cover the first few variant of this COVID-19. Okay, we don't know the newer one. We don't know the newer one. Okay, so stay safe. Okay, stay safe. Okay, let's come back here. So let's see. So do bed nets appear to be effective? Now, so we have two different, sounds like we have two claims here. This is the formal claim that the incidence of malaria is lower for infants who use bed nets. Okay, do bed nets to appear to be effective? You can use either one. Okay, let me use the one they say to test the incidence of malaria is lower for infants who use the bed nets. Hypothesis. Let's say the one using bed nets is group 1, not using bed nets is group 2. Okay, so the hypothesis is the one using bed nets has the lower proportions of malaria incidence compared to the one without bed nets. Okay, now remember I told you that about the vaccination earlier. This is how we also see the effectiveness of that vaccine. Okay, the effectiveness of that vaccine. Now, but you know that if you get the vaccine and you still get COVID-19, you cannot sue the company that make the vaccine, right? You know that, right? Why? Well, because they are responsible for certain type of strain, certain variation of COVID only, not the newer variations. In other words, basically this, you catch COVID-19 or not, it's still you. Okay, you cannot blame anybody. And even if you can blame anybody, you are the one getting it. Okay, so if you are the one actually get the effect of catching COVID or not, getting malaria or not, why don't you then be more proactive in taking care of yourself instead of asking other people what to do? Okay, there's a balance between personal freedom and I don't want to say logic as if people with personal freedom has no logic. I cannot enforce other people, not even my students, on what you're supposed to do with your daily life in protecting yourself. Okay, but I can share with you, hey, you know what? This is the one I think will work. Okay, so in the end, will the vaccine work? Not 100%. Will mass work? No, not 100%. Okay, but the combination of those may be strong enough to protect you more. Okay. Then because the other side has no constant, I need to set one side to constant. I subtract both sides by P2. So this is a left tail. This is the claim, and it is a left tail test. Okay, now let's do further setup. We need to find the P hat. P1 hat, P2 hat, and P bar. Do you remember that? Okay, P1 hat, P2 hat, and P bar. Now let's just use calculator right away. I will plug in these numbers to help me computing them fast. Okay, so I go to stats, tests, to proportion z test. I hope you remember which one is that. Okay, x1 is 15 and 1 is 343. X2 is 27, N2 is 294. And we want to show that P1 is less than P2. Okay, that's our number. Okay, that's our number. Let me screenshot that and then put it somewhere so that I don't need to keep on quoting that. Keep on going back to my calculator view. Let me put it. Let me put it here. Okay, so my P1 hat is 0.04373. My P2 hat 0.09184. Now my P bar is 0.06593. Now Q bar, therefore, 0.93407. Okay, let me move this to other side. Step 3. What is my test statistic? C equals to P1 hat minus P2 hat. Minus 0, big over square root of, this will be long, P hat, P bar 0.06593 times 0.93407 over N1, that's 343, plus 0.06593, 0.93407 over the sample size for the second group, 294. And according to our calculator, the C-score is, see, that's the good thing about you knowing how to use calculator, right? This is equal to negative 2.43892. Okay, now step 4. How about the p-value? The p-value, let's see the standard normal distribution. That's negative 2.43892. So the p-value is normal CTF negative E99, negative 2.4389201, and that will be, the p-value is 0.007365. Okay, remember calculator, we can use calculator only to get step 3 and step 4 actually. Okay, you still need to set it up. Okay, you still need to set it up. You still need to conclude that. Okay, step 5, informal conclusion, reject null hypothesis. Now the p-value is so small such that even if alpha is 1%, you still reject null hypothesis, right? The alpha is, yeah, the alpha is 1% here. Okay, so we still reject null hypothesis. So conclusion, at 1% significance levels, at 1% significance level, there is sufficient evidence The wording, the wording in practice, they may say this way: there is very significant evidence. Instead of using the word sufficient, they will say there is very significant evidence to support the claim that. Why? Because it's at 1% significance level, right? So they use the word very. Okay, they use the word very, significantly sufficient evidence, or simply very significant evidence to support the claim. The claim that the incidence of malaria is lower. Is it the wording? For infants who use bed nets. So to answer the last question, do bed nets appear to be effective? Then you conclude that and bed nets appear to be effective. Okay, that's the follow-up from the conclusion to answer that last question explicitly. But of course, from the statistic, we also see that bed nets, even though it is effective, it doesn't mean nobody will get malaria once you use bed nets. No, it's not effective in that sense. It is not effective such that you don't catch malaria at all. The vaccine is not said to be effective because nobody will get COVID after that. No, that's not what they meant by being effective. Okay, what they meant by being effective is that when you have, if you are vaccinated, or in this case, if you use bed nets, the incidence of you having malaria, the infant having malaria, or that person catching COVID is much lower. Okay. I actually prefer to say that in case of COVID, in reality, it's not that the chance that they catch COVID is lower, but the viral number, the chance that the virus can actually replicate fast and put you and knock you down to be hospitalized is much lower. Okay, there's a chance that you catch COVID, but you don't even show any symptoms because you are already vaccinated. That's what I'm saying. Okay, that's what I'm saying. Number 5. I will do this one more problem and then we will go to break. Okay, in a study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are given in the accompanying table. The values are before and after hypnosis. The measurement is in centimeters on a pain scale. Assume that the data come from a population that is normally distributed. Okay, that's the data. Part A, find the difference in the last row. So you will do the subtraction before minus after, right? Negative 0.2. This is 4.1. This is 1.6. Okay, so before, if the before is more, it's more painful compared to after hypnosis. More painful compared to after hypnosis. Okay, but honestly, instead of doing it that way, let me do it differently. we will use calculator anyway. So let's just plug in the numbers into calculator. Okay, so I go to stats, edit. Oh, column 1, 2, 3. Clean it up first. Stat clear list, list 1, comma, list 2, comma, list 3. Clean it up. Okay, we are ready to go. So list 1 will be the numbers from before, 6.6. That's the first data. 6.5, the second data. 9.0, the third data. 10.3, the fourth data. 11.3, the fifth data. 8.1, the sixth data. 6.3, the seventh data. 11.6, the ninth, the eighth data. Am I skipping anything? Let me check. So the first one is 6.6, 6.5, 9.0, 10.3, 11.3, 8.1, 6.3, 11.6. So there are 8 data, okay, for the first row before and next. The next row, 6.8, 2.4, 7.4, 8.5, 8.1, 6.1, 3.4, 2.0. Now, then our L3, you move to L3, go up to the heading, to the header, and then you do L1 minus L2. Then it will occupy that for you. Now, I know that if you only need to fill up this row here, you just do it manually. There are only 8 subtractions to do. But the thing is, after that, we will compute the sum of these squares, right? And instead of doing that one by one, I think I will just use calculator. Okay, I will just use calculator. So the next one is what? 1.8, 3.22. 1.8, 3.22, this is 2.9, and this is 9.6. Okay, go back to my calculator. I need to find the sum of D squared. Go to stat, calculate, one var stat, list number 3, which is already there. Okay, let me screenshot that so that I don't need to go back to that calculator again and again. Let me put it here for now. Okay, so the sum of D is 25. The sum for D squared is 137.46. Find the mean and standard deviation. So the mean X bar will be, the mean for differences is D bar, not X bar. D bar equals to 25 over 8. That's 3.125. Standard deviations, sample variance of the differences will be 8 times 137.46 minus 25 squared over 8 times 7. Now use your calculator. 8 times 137.46 minus 25 squared divided by 56. That's 8.47643. 8.47643. Okay, now then the square root of that will give us our standard deviation. But Thomas, I thought we already have that standard deviation. Yes, but I still need to show the work, right? Okay, so I pretend to show the work even though I know the standard deviation of the differences is given to me here. Okay. Now, the reason I still show the work, at least I want to make sure that I get it right. My sample variance of the differences is the same. Okay, take a look. That's the same, right? 2.91143. Okay, now I can get rid of this. Now, that's for part C. Let's go on to part D. Use alpha equals to 5% to claim that the sensory measurements are lower after hypnotism. So step 1, claim. The sensory measurement are lower after hypnotism. Hypothesis. What happened? Null hypothesis, alternate hypothesis. So mu1 is greater than mu2, maybe before and after. After hypnotism, the measurement is lower. So mu after is less than mu before. Okay, so this is my B for before, this is my A for after. Okay, so this is mu before is less than equals to mu after. But again, this is, we don't have constant on the other side, so we have to modify this. So mu before minus mu after is less than equals to 0. Mu before minus, I'm sorry. Yeah, mu before minus mu after is greater than 0. And this is a match pair. So we are actually looking at the MD, the mu D. Okay, that's the hypothesis. Step 3, test statistic. T equals to D bar 3.125 minus mu D, which is 0, over SD, which is 2.91143 over square root of 8. You know what? I use my calculator again. I go to stat, test, T test. Okay. And then, oh, don't you think they're really nice? The mu 0 already there, X bar is this, sample standard deviation is this, sample size is this, and we want to be greater than 0, greater than 0. Okay, so the T score 3.03591. 3.03591. That's the test statistic. Okay, step 4, P value. That's T distribution. The test statistic is 3.03591. So the P value is TCDF 3.03591 E99 degree freedom 7. But we have the p-value here, 0.00948. 0.00948, which is less than 1%, right? What is the alpha, by the way? 5%, as I remember. The alpha is 5%. So let me do it here. Step 5, informal conclusion. Reject null hypothesis. Okay, conclusion. At alpha equals to 0.05, there is sufficient evidence to support the claim that the sensory measurements are lower after hypnotism. Okay. To make the situation more complete, let's do 4B, critical value. 5% right tail. So T critical is equal to inverse T area to the left, 0.95, degree of freedom 7. That will be 1 point something, 1.89458. And my test statistic is much higher than that. It's in the tail. I somehow think in the previous page, I forgot to do the critical value. Yeah, I forgot to do the critical value for that. Let me insert that here. So 4B critical value. We want alpha to be 1%. We want alpha to be 1%, its left tail. Okay, so C critical equals to inverse norm 0.0101. I think that's negative 2.32 something. 2.32635. Now that's for question number 4, number 5. Okay, this is page 4. We have 3 pages to go. Let's see this number 6. I set it up and then I give you a break. Instead, I'm planning to give you a longer break. Basically, the break 10 minutes, and then I would like you to try to do this problem. Okay, in the randomized, double-blind, placebo-controlled trial on children. Double-blind means what? Double-blind means the person who receive the treatment don't know if they get the real treatment or they get the placebo. And also means the person who give the medicine don't know if that medicine is the real medicine or a placebo. So you see that there's somebody who administer the medicine, and the patient, right? Okay. Now there's the supervisor, or the person who knows. Okay. Basically, that's usually the statistician. Okay. Supervisor is the one knows if the medicine given is the real, in this case, echinacea, or just placebo. Okay, but the person who administered that, let's say the nurse, don't know. The patient who received that also don't know. That's what it means to be double-blind placebo control. Okay, that's what it means to be double-blind placebo control. So we compare that to those people who don't get the medicine, but they are given a fake medicine, let's say just some kind of flour inside the pill, right? Inside the capsule, okay, and see the type of effect. Okay, now echinacea was tested as a treatment for upper respiratory infection in children. Now, the number of days with fever was one criterion used to measure effects. Okay, so we have two groups here, the one with echinacea. Sorry if I don't read it right. I don't know how to read it correctly. So the N is 337. The mean number of days with fever was 0.81. With standard deviation 1.50 days. Okay, now of those people, children with placebo, 370 of them, the mean number of days with fever is 1.46 days with standard deviation 1.16. Okay, with the alpha equals to 0.05. Test the claim that echinacea affects the number of days with fever. Okay, that's what you need to do. So right now it's 5:30. Let's take 10 minutes break and another 10 minutes for you to go as much as possible for this question. We come back at 5:50. Okay, go as much as possible for this question. Okay, and then we start again at 5:50. Now I may start working on this problem before 5:50. Okay, I will start. Notice the following. The claim that we are testing is that the echinacea affects the number of days with fever. So affecting maybe in the way to shorten that, maybe increasing that. Right? Okay, so when we test the claim, the hypothesis, will be mu1 is not equals to mu2, as opposed to the null hypothesis that it doesn't affect. Okay. Now then we need to modify the hypothesis. Let me continue here. So H0 is mu1 minus mu2 equals to 0. H1 to be mu1 minus mu2 not equals to 0. Now, what I need you to be aware of is that the last sentence, based on the result, does echinacea appear to be effective? Now, when we say echinacea being effective, means the mu1 is less than, the average day with fever is less than to the one average with placebo. Right? So those are actually two different questions. Okay, those are actually two different questions. Now, what I need you to be aware of this, there are two possible ways to do the claim. Okay, in this case, if you do the claim coming from here, if this is what you say with your claim, then it has to be two-tailed. But if your claim is echinacea appear to be effective, then the hypothesis later on will be one-tailed. You see what I mean? It's not two-tailed. It's not two-tailed. So it depends on what you say in your claim. Now, from here, I actually want to teach you one thing. You may say the claim is affect the number of days with fever, but then in your step 6 later on, you may say echinacea appear to be effective, which was not what you did, what you test. You were testing the claim if the echinacea affects the number of days. Okay, so your conclusion cannot be about it is being effective to reduce or lessen the number of days with fever. Okay, you see that how people do one thing, they claim one thing, but they conclude another thing. The claim is two-tailed, but be very careful that your conclusion should not be echinacea appear to be effective or not. No, that should not be your conclusion. Your conclusion should be the claim. So if your claim is this, then consequently, your hypothesis will be two-tailed. Okay, this is the claim. And that's two-tailed. So how do we answer the last question, Thomas? Let's see later on. Okay, let's see later on. So test statistic. We don't know population standard deviation, so we use T. Test statistic will be x1 bar 0.81 minus x2 bar 1.46 minus mu1 minus mu2, which is 0, over square root of S1 squared over N1 plus S2 squared over N2. Okay, I will just use my calculator. I do the test right away. So stats, test, this is 2 sample t-tests. Right? So you need to know what to use if you use a calculator. Okay, now then I will input the statistic. The x1 bar is 0.81. The sample standard deviation for the first group is 1.5. Sample size 337. X2 bar is 1.46. The standard deviation is 1.16. The sample size is 370. We are testing two-tailed. Okay, no, it's not pool. And calculate. So the t-score is negative 6.4005. Negative 6.4005. 0050. That's the test statistic. Okay, step 4, p-value. Okay. That's negative 6.40050. But that will be two-tailed, right? So I will need to multiply by 2. So the p-value is 2 times TCDF negative E99 negative 6.40050. Degree of freedom is, use the smaller one, 336. Okay, so according to this, I will have p-value 3 point something e to the negative 10. This is 3 point something 02 times 10 to the negative 10. That's effectively 0. That's the p-value times 2. Forgot to multiply by 2. But say 10 to the negative 10 means the 6, this is 6.04 something times 10 to the negative 10, right? It means the 6 here is at the 10th decimal place. That's very small. Okay, effectively 0. So step 5, informal conclusion. We will reject null hypothesis. In step 6, conclusion. What is the alpha again? I think it's 5%, right? At 5% significance level, there is sufficient evidence to support the claim that echinacea affects the number of days with fever. Okay, now does it mean echinacea is effective? Does it mean echinacea is effective? Let's see that. For echinacea to be effective, then in your step 2, mu1 has to be less than mu2, which implies mu1 minus mu2 is negative. That gives us a left tail. Okay, that gives us the left tail. Now the p-value for that tail according to our computation is 3.02 times 10 to the negative 10, which is effectively 0. Okay, which is still less than alpha. Okay, which lead to rejection reject null hypothesis. So echinacea appears to be effective. That's the question, right? Okay. Basically, the fact that echinacea affects the number of days with fever, and to say that it is effective, which means it's reducing the number of days with fever, those are two different claims. Now, what I'm trying to show you here is, even though they are different claims, okay, but our data are the same, which give us the same test statistic. Okay, the same test statistic. Now, because of that claim, it gives us either the hypothesis is two-tail or one-tail. Two-tail for what we had earlier. One-tail if the claim had been echinacea to be effective. Now, if it is only one tail, then the p-value, you don't need to multiply by 2 anymore. It's only one tail, right? Okay, which is less than alpha. Which means we still reject null hypothesis. Okay, but notice that the conclusion is not that echinacea affects the days, number of days anymore. The conclusion will be that there is sufficient evidence to support the claim that echinacea is effective. Echinacea appears to be effective. Okay, now for extra credit, 4B. Critical value. This is two tails, by the way. So this is negatives. I'm sorry. We want 5%, right? So find the critical value, negative t critical, such that the area of the tails is 5% in total, 2.5% each. So the t critical is inverse t, area to the left 0.975, degree of freedom, use the smaller one, 336. I get, this is, oh, it's plus minus, by the way. It's plus minus 1.96705. Okay, and our test statistic is -6, which is at the tail. That's why we reject null hypothesis. So when I gave this test, I remember I gave this question twice. I think I gave that in fall, and I also gave that in summer. And in both times I gave this test, I have students saying, but Thomas, what is the claim supposed to be? Is the claim to be effective or the claim to be affecting the number of days? Because, I mean, I'm talking about these are smart students, okay? Students who are actually passing. I mean, they are in test 4, right? So they actually survived test 1 to 3. And they wonder, so what should I use for the claim? I say, just use either one, okay? But you know, there are actually two different claims there. Whichever you use, it will affect your hypothesis. So there are actually two answers for this number 6. Okay, what they ask actually, does echinacea affects the number of days with fever? That's the claim they want you to test. Okay, and the follow-up question, does echinacea appear to be effective? That's the follow-up question. Okay. Now, as you can see here, I did that follow-up question using the number. If that results in different claim and therefore different hypothesis, but test statistic is the same. Okay, the p-value will be the same or multiplied by 2. Depends on one tail or two tail. Okay. Page 6. In a survey of commuting mode, it was found that among 1,068 homeowners, 82.4% drive themselves to work. So homeowners, okay, the N is 1,068. Now, what is that 82.4% representing? That's the P1 hat. That's the proportion in among that 1,068. Okay, while among 1,064 renters, the proportions that drive themselves to work is 68.1%. Now, based on the result, does there appear to be a significant difference? Now, that tells us that's 5%, right? Between the proportion of homeowners who drive to work and the proportion of renters who drive to work. Okay, that's the claim. That's the claim. The claim, there appears to be a significant difference between the proportions of homeowners and renters who drive to work. Okay, now let's go back to the setup first. We need to find the p-bar, right? We need to find the p-bar. But to find the p-bar, we need to have x1 plus x2 over n1, which we have, plus n2, which we have. But we don't have x1, we don't have x2. How to find those? Well, what we will do is, remember that p1 hat is actually x1 over n1, right? Which means x1 is n1 times p1 hat. That's 1,068 times 0.842. I get 899 point something. Usually we round it, okay, because this is the number of successes, right? So we will use 899. We will use 899. While x2 will be n2 times p2 hat, which is 1,064 times 0.681. That is 724.58 something. We do rounding, that's 725. Okay, so later on I will use calculator for that. Okay, hypothesis. significance difference. So the alpha is 5%. Even though you don't know what is the significance level being used, by default it is 5%. Okay, the hypothesis, null hypothesis, alternate hypothesis, P1 is not equal to P2. Difference, right? Okay, null hypothesis, then they are equal. This is the claim, and it is two-tailed. Step 3, test statistic. I already have the P1 hat, P2 hat, so Z equals to P1 hat 0.824 minus P2 hat 0.681 minus P1 minus P2, that's 0 over square root of, now I need P bar, Q bar. Let's use calculator to compute that. Okay, I go to stat test to proportion C test right away. Okay, so X1 is what? 899. N1 is 1068. X2 725. N2 1064. We are testing two-tail. Calculate. Ding. Okay, so my P hat is, let me write that my P hat here. So P bar is 899 plus 725 over 1068 plus 1064. My P bar is 0.76173. 0.76173. So Q bar is 1 minus that. Zero 0.76173 times 0.23827 over 1068 plus copy paste. Now, the good thing is if you use calculator, then you can see the C-score right away there. That's 8.69053. 8.69053. Oh, that's a very, very big one. Okay, and the p-value is two-tailed, right? It's two-tailed. This is 8.69053, but you need to double it. That's 2 times normal CDF. 8 times 69053 E9901. That will give us, let's see, what's that? 3.655, 10 to the negative 18. 3.655 times 10 to the negative 18, that's practically 0. Okay, so step 5, informal conclusion, reject null hypothesis. Yeah, because the p-value is so small already, right? Super small. So, and step 6, conclusion. at 5% significance level, there is sufficient evidence to support the claim that there appears to be a significant difference between proportions of homeowners and renters who drive to work. Okay, that's for number 6. Now let's take a look on the test statistic. I'm sorry, critical values, 4B. Critical value. It's two tails, so I use critical values. That's standard normal distribution. The area of the tail is 5% divided by 2 tails. That's 2.5% each. So C critical is plus minus inverse norm 0.97501, which will give us plus minus 1.95996. That's the critical values. Oh, the last page, question for CLO. CLO is course learning outcomes. These questions was from our from the math department at East LA College. So they asked me, Thomas, can you put this question in your class? In your class, we would like to see the result. Okay, we'd like to see the result. So this question number 1 is 4 point, and number 2 later on, question 2 you see below is 6 point. Okay, so let's work this out. The Los Angeles Beanstalk Club has a height requirement that women must be at least 68 inch tall. Now women's height are normally distributed, so let X be women's height. This X is normally distributed with mean 63.6 inches, standard deviation 2.5. Okay, what percentage of women meet the requirement? Per probability or percentage meet the requirement is equals to the probability that the height is at least 68. That is normal CDF, right? So you have standard, you have normal distribution whose mean is 63.6. You need 68 or more. Okay, so that's normal CDF 68, E99, The mean is 63.6, standard deviation 2.5. Oh, this question is not hard. And you use your calculator. I get, 0.03920. Oh, so only around 4%. So only around 4%. Okay, I expect more. Okay. Why we have 4 points? The 4 points actually consist of, first, the probability notation, at least this one. Okay, the density curve, the way to compute that, either you use calculator or you use conventional method, and then of course the final answer. Those are the breakdown of those 4 points. Next, number 2, California speeding. A simple random sample of 40 recorded speeds is obtained from cars traveling on a section of Highway 405 in LA. So n equals to 40. The sample has a mean, okay, that sample mean is 68.4 and standard deviation 5.7. How do you know the standard deviation is from sample, Thomas? Because it says the sample has this mean and this standard deviation. So this standard deviation actually belongs to the sample, right? So how will the wording be if the standard deviation there is supposed to be from population? Well, they have to say that it is from population. They will say, let's say the sample has a mean of 68.4 miles per hour, and it is known the overall standard deviation of the of speeds is 5.7. They use the word overall or the word population. Okay, now use a 5% significance level to test the claim that, so hypothesis testing. So step 1, claim. The mean speed of all cars is greater than the posted speed limit of 65 miles per hour. Hypothesis. Null hypothesis, alternate hypothesis, mu is greater than 65, mu is less than equals to 65. This is the claim, and that's a right tail. Step 3, test statistic. Let me turn off my calculator first. Test statistic. So Z, no, it's not Z, it's T. T equals to the sample mean 68.4 minus the mu 65 over sample standard deviation 5.7 over square root of 40. So 68.4 minus 65 divided by 5 points, parentheses 5.7 divided by square root of 40. I get 3.77254. So the p-value, the 6 points actually refer to 6 steps of this work here. So that's a right tail. So p-value is TCDF 3.77254, E99, degree of freedom 39. Two, 0.00027. On my calculator, I see 2.68 something times 10 to the negative 4. So I write it in decimal, okay? Not in scientific notation. Okay, I don't know what's the alpha though. I forgot. Yeah, 0.05. So the informal conclusion, reject null hypothesis. And then the conclusion is at 5% significance level, there is sufficient evidence to support the claim I don't have enough. That the mean speed of all cars is greater than the posted speed limit of 65 miles per hour. Okay, extra credit. How about the critical value? T critical on the right tail, the area is 5%. So T critical is inverse T. Area to the left, 0.95, degree freedom, 39. $1.6848. Okay, I'm done with this one test. I hope you can study from this. Try to do it on your own also, okay? Because there are some aspects. First, you need to really master the structure, 1, 2, 3, 4, 5, 6. You need to know how to use calculator. You need to know when to use which test statistic. You need to know how to express the hypothesis test, how to find your p-value, and all the related calculator work, okay? Now, let me remind you that for your test 4, we do not start from 4:30, not from 4:30 p.m. but from 4 o'clock. Okay, so please go on Zoom even earlier if possible. I can give you extra time, but I cannot give you extra time at the end. I can give you extra time at the beginning. Why? Because so your test will be from 4 o'clock, not to 6:30 p.m., but to 7 p.m. So you, instead of having 2 hours, I give you 3 hours. Okay. Now the thing is, even I don't mind to give you even more time, but I have another test for my Calculus 2 class after your class. So I cannot extend your time. Okay. See, when you end at 7 p.m., then I still need to supervise you to submit that up to 7:15, right? Okay. Now their class start at 7:20. I have only 5 minutes to change from your class to their class. You see what I mean? Okay. So if you want more time, then go on Zoom earlier. Now, my office hour is start from 3 o'clock. Okay, my office hours start from 3 o'clock. I think I don't mind to start at 3:40. Okay, to make it short, and instead of from 4:30 to 6:30 p.m., we actually have from 4 o'clock to 7 o'clock p.m. Okay, that's for your test 4. Okay, that's for today. On Friday, I will have I hope I have enough time to go over one more test with my other class, my Friday class. And then I will actually post it on YouTube so that you can watch it. Okay, I will also post your recording here to YouTube for them to see. Okay, so this is test 4 for Monday, Wednesday class. Okay, later on for my Friday class, at East LA College, that will have from 8:20 to 11:20. That will be their test time. Okay, that's for them. So they get 3 hours, maybe earlier. I may start with them earlier. Some of them usually take like 10 minutes earlier. Okay, but 10:20, I need to be done with them. Okay, anyway, I need to stop here. Bye-bye.